Dear children, today we'll start third chapter, that is current electricity. So first we'll start what is electric current. What is electric current? First tell me, what do you mean by current? Current means that is the rate of flow. So here, what is electric current? The rate of flow of what? So here as it is electric current, so it is a rate of flow of electric charge across any cross section of a conductor. So the electric current is the rate of flow of electric charge across any cross section of a conductor. So before we have completed electrostatics. Electrostatic means charges at rest. So suppose it is the conductor, then here charge flows. So when charge flows, so in electrostatic situation, there is no macroscopic movement of the electric charge when conductor is equipotential. But when you apply potential difference across the conductor, then the charge particles move. So in a conductor, which charge particles will move? You know, proton will not move because that is strongly bound within the nucleus. Then which electrons can move? Then which electrons can move? Not the inner electrons or which are bound to the nucleus or inside atom, those electrons cannot move. Then the free electrons can move. Then the free electrons will move. You remember, the free electrons will move from lower potential to higher potential. If it is higher potential, it is lower potential, the electrons will flow from this lower potential to higher potential. So when the electrons will move from lower potential to higher potential, then we have to assume equal amount of positive charge will move from higher potential to lower potential. When the charge moves, then current is produced. Then what is the electric current? That is the rate of flow of electric charge across any cross section of a conductor. If it is a conductor, if this potential is V1, it is V2. If V1 more than V2, then electrons will flow from lower potential to higher potential. Then we will assume equal amount of positive charge will move from higher potential to lower potential. So now, if you consider a cross section at here, so now, what is electric current? If del Q, now only consider the flow of positive charge, not the flow of electron. The positive charge flows from higher potential to lower potential. If del Q is the amount of charge flows in time del T, then what is the current? I is equal to del Q by del T. If the flow of charge is not uniform, if charge flows at non-uniform rate, means if first second if Q one amount of charge flows, then in second suppose Q2 amount of charge flows. That means the charge flow is non-uniform. Then the current at a particular time, that is called as instantaneous current. So for non-uniform flow of electric charge, for non-uniform flow of electric charge, instantaneous current, instantaneous current, that is I is equal to limit. You know, whenever the instantaneous word comes, the limit delta t tends to 0. Delta q by delta t, that equal to dq by dt. That is the time derivative of electric charge. So now come to what is the direction of electric current. Direction of electric current. By convention, it is supposed where it is A, it is B, let it is at higher potential, it is at lower potential, we will assume the current flows from higher potential to lower potential. The direction of electric current, that is from higher potential to lower potential, that is along the flow of positive charge. It is by a convention, or you can say it is a conventional current. Then what is the direction of flow of electron? Electrons flow in the opposite direction of electric current, that is from lower potential to higher potential, or you can say it is the electronic direction of electric current. If I will ask a question, if Q is equal to, Q depends upon time as 2t square plus 5t plus 10 coulomb, then what is the electric current at t is equal to 5 seconds? As we know, I is equal to dq by dt. You take the derivative of this, d by dt of 2t square plus 5t plus 10, that equal to, you know, its derivative is 4t plus 5, and its derivative is 0. At t is equal to 5 second, I is equal to 4 into 5 plus of t, you write 5, so plus 5, that equal to 25 units. SI unit of electric current is ampere. Coulomb is in SI, so it is 25 ampere. So now, here electric current has the magnitude, electric current has the direction. You know, a vector quantity is the quantity which has both magnitude as well as direction. So electric current will be a vector quantity or not. You remember, though electric current has both magnitude as well as direction, but it cannot be considered as a vector quantity because it doesn't obey the law of vector addition. You know law of vector addition. So you remember, current is a scalar quantity. You see, it is a wire, it is another wire, it is a wire, it is a junction. If here 5 ampere of current is coming, here 10 ampere, suppose the angle between them is 60 degree, then what will be the current flowing through this branch? So definitely we will say 10 plus 5, 15. Whatever the angle will be. Always the current will be this plus this. That is algebraic sum. That is scalar sum. Directly addition 10 plus 5. Not here we will take the vector addition like magnitude r is equal root over of a square plus b square plus 2ab cos theta. So as it doesn't obey the law of vector addition, so we will consider electric current is a scalar quantity. Now come to unit, SI unit. I is equal to del q by del t. So SI, do you remember it is ampere? Ampere, symbol is capital A. Therefore 1 ampere is 1 coulomb by 1 second. Charge unit is coulomb, time unit is second. So how can we define ampere, 1 ampere? So you can say current flowing through a conductor is said to be 1 ampere if 1 coulomb of charge flows across any cross section in 1 second. Now come to dimension. What is dimension? You remember current is a fundamental unit in SI. Though here we have written I is equal del q by del t, we will assume current is a fundamental quantity, because fundamental quantities are those by the help of which we can represent other physical quantities. So in magnetism, all the magnetic quantities are explained in terms of current. That's why we have taken current as a fundamental, not charge as a fundamental. You remember. So its dimension, you remember, current as the dimension, you know it is A. So now come to Ohm's law. What is Ohm's law? You remember the current flowing through a conductor, it is a conductor, let it be V1, V2, let it be V1 more than V2, let V is equal to V1 minus V2. Then current I will flow from higher potential to lower potential. So you remember the current flowing through a conductor is directly proportional to the potential difference across the two ends of the conductor, provided the temperature and other physical conditions remain same. Other physical conditions means mechanical strength, means area, cross section, length, etc. remains same. So you remember Ohm's law, current flowing through a conductor is directly proportional to the potential difference applied across the two ends, provided temperature and other physical conditions remain same. That is I proportional to V, or I is equal to V by R. where R is equal to resistance of the conductor. The proportionality constant R is called as resistance of the conductor. If we will draw the graph between potential difference versus current, the graph will be straight line, as here V proportional Y or I directly proportional to V. It is all about your Ohm's law. Next we will discuss about resistance.